presenting my visually impaired presentation on the topic organometallic compounds. Organic compounds in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metals, that is lithium, sodium, magnesium, zinc, mercury, lead, cadmium, form such compounds. The organic part is generally an alkyl, alkenyl, alkynyl, or an aryl group. They are named simply by adding the name of the metal to the name of organic group linked to the metal. For example, CH3Li is methyl lithium, C2H5MgBr is ethyl magnesium, CH3CH2 whole twice 3 Li is n-butyl lithium, and CH2 whole twice CH2H5 whole twice Hg is diethyl mercury, C2H5 whole 4 Pb, this is tetraethyl lead, and C6H5 Li, this is phenyl lithium. CH3 whole twice cadmium is dimethyl cadmium, C2H5 whole twice zinc is diethyl zinc. Carbon metal bond in organometallic compounds differs widely, varying from bonds which are essentially ionic to those which are largely covalent. For example, C negative M plus is largely ionic, and C delta minus plus delta M delta plus on metal is metal where lithium is magnesium. So carbon metal bond is largely covalent, in which metal is mercury, lead, and tin. The extent of ionic or polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the metal, more is the ionic nature of the carbon metal bond. In general, the ionic nature of the carbon metal bond follows the sequence: carbon potassium, then carbon sodium, then carbon lithium, then carbon magnesium, then carbon aluminum, then carbon zinc, then carbon cadmium, then carbon mercury. The reactivity of organometallic compounds also depends upon the nature of the carbon metal bond. Generally, the larger the ionic character of carbon metal bond, more reactive is the organometallic compound. Our compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of their reactions. Organometallic compounds are extremely useful for the synthesis of a vast variety of organic compounds. Apart from these, many of the organometallic compounds are commercially important as well. For example, tetraethyl lead is extensively employed as an anti-knock agent. Organotin compounds are used as antioxidants in rubber products, and phenyl mercuric acetate is used as a fungicide and disinfectant, and organoarsenic compounds are used in medicines. Now, first come on to the organomagnesium compounds, that is Grignard reagents. Organomagnesium halides are extremely important reagents in synthetic organic chemistry. These reagents are commonly known as Grignard reagents after the name of discoverer Victor Grignard, who received the Nobel Prize in 1912 in chemistry for this discovery. The general formula of Grignard reagents is RMGX or ARMGX, where R represents an alkyl group and AR represents an aryl group. Preparation: Grignard reagents are prepared in the laboratory by the action of an alkyl or an aryl halide, preferably bromide or iodide of magnesium metal, that is Stirling's in dry ether. Rx plus magnesium in the presence of dry ether gives RMGX, that is alkyl magnesium halide. CH3I in the presence of magnesium in dry ether gives CH3MgI. Besides ether, tetrahydrofuran, dioxane, dimethylethane, or dimethyl ether of diethylene glycol, tertiary amines can also be used as solvents. In fact, THF is considered to be the best solvent since it increases the reactivity of an alkyl or an aryl halide towards magnesium. It is because of this reason that the Grignard reagents of less reactive aryl and vinyl halides, which are difficult to prepare in ether, are prepared in THF. Bromobenzene plus magnesium in the presence of dry ether giving phenyl magnesium bromide. Chlorobenzene in the presence of magnesium in THF gives phenyl magnesium chloride. Further, it has been found that for a given alkyl group, the ease of formation of Grignard reagents is of the order iodide, bromide, and then chloride. The alkyl or aryl magnesium fluorides are, however, unknown. For a given halogen atom, the order of reactivity is H3X, C2H5X, CH3H7H, X, etc. In the formation of Grignard reagent becomes increasingly difficult with increase in the number of carbon atoms in the alkyl group. The use of tertiary alkyl iodides is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chlorides may then be used. Procedure for the preparation of Grignard reagents: alkyl or aryl halide is added slowly to a perfectly clean and dry flask containing dry magnesium turnings covered by a layer of absolutely dry ether or THF. Reaction mixture is warmed a little when an exothermic reaction should soon start. If the reaction does not start within 5 minutes, the few crystals of iodine are added and the reaction mixture is warmed a little. A vigorous reaction soon sets in and magnesium gradually dissolves, forming a cloudy solution of the Grignard reagent. Precautions in preparation of Grignard reagents: During the preparation of Grignard reagents, following precautions must be observed. The apparatus should be perfectly dry and protected from moisture by using a CaCl2 guard tube. All the reagents and solvents, alkyl or aryl halide, magnesium metal, and the ether must be absolutely dry. Ether used as a solvent must be completely free from alcohol. This can be done by first washing ether several times with water, followed by drying over anhydrous calcium chloride for 1 to 2 days and subsequent distillation over sodium. An atmosphere of dry nitrogen free from oxygen and carbon dioxide should be maintained throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by moisture water and react with oxygen and carbon dioxide to form alcohols and carboxylic acids, respectively, vide infra. The ethereal solution of Grignard reagent thus obtained is generally used as such for various reactions by adding it to the other reagent. Mechanism of the formation of Grignard reagent is still not certain. According to the Gomberg and Bachmann, the reaction commences with the formation of a small amount of magnesium halide and then proceeds by a free radical mechanism, in which Rx plus magnesium plus Xr giving Rr plus MgX2 and MgX2 plus Mg giving 2 MgX radical, Rx plus MgX radical giving R radical plus MgX2, R radical plus MgX radical giving R MgX. This reaction also elegantly explains the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium and iodine. Structure of Grignard reagent hasn't been finally settled so far. Recent research has shown that actual structure varies with the particular Grignard reagent and the solvent used for the preparation. Grignard and Blaise observed that evaporation of ethereal solution of Grignard reagent resulted in a white solid having the composition RMgX 2C2H5O. They suggested that ether molecules were present as ether of crystallization. X-ray analysis of these dietherates suggests that the four groups are arranged tetrahedrally as shown in this figure. Thus, Formula 1 represents that ether doesn't merely provide a medium for the reaction, but it also helps to dissolve the reagent formed due to solvation by ether molecules. This is supported by the observation that Grignard reagents can be prepared even in benzene solutions in presence of a tertiary amine which coordinates with magnesium like ether and thus dissolves it. Further, Formula 1 shows the Grignard reagent in the monomeric form, but physical studies have revealed that Grignard reagent exists as a 1:1 complex of a dialkyl or diaryl magnesium and magnesium halide coordinated with molecules of ether. These two species are held together by halogen bridges as shown in Formula 2. R2Mg.MgX2 giving R2Mg plus MgX2 in equilibrium with 2R-MgX Grignard reagent. However, for the sake of convenience, the formula RMgX has been used to represent alkyl magnesium halides in the text. Carbon-magnesium bond in the Grignard reagent is highly polar due to large electronegativity difference between carbon and magnesium. 2.5 minus 1.2 giving is 1.3. Consequently, due to greater electron density around carbon, the alkyl group in Grignard reagent can act as a carbonyl or a nucleophile, that is, it can attack any electron deficient center in other molecules. In other words, Grignard reagents chiefly undergo nucleophilic substitution or nucleophilic addition reactions. Nucleophilic substitution reactions. Grignard reagents react with compounds containing an active halogen or hydrogen atom. All such reactions involve the nucleophilic attack of the alkyl of the Grignard reagent on the electron deficient center as shown below. RMgX plus AB giving Ra plus MgBx. Nucleophilic addition reactions. Grignard reagents react with compounds having a multiple bond such as C double bond O, C double bond S, S double bond O, C triple bond N to form addition products which when hydrolyzed yield a vast variety of compounds. In all such reactions, the addition of the nucleophilic group of RMgX R negative occurs at the more electropositive end and that of MgX group at the more electronegative atom of the multiple bond. Thus, C double bond O plus RMgX giving CrOMgX, which hydrolyzes to give COHR plus MgOHX. Synthetic uses of Grignard reagents. Grignard reagent serves as extremely valuable starting materials for the synthesis of a vast variety of organic compounds. They have attained a position in synthetic organic chemistry unrivaled by any other class of compounds. To illustrate this, some important synthetic applications of Grignard reagents are described below. Alkanes. By action with the active hydrogen containing compounds. Active hydrogen containing compounds such as water alcohols, thioalcohols, carboxylic acids, hydrogen sulfide, ammonia, amines, primary, secondary but not tertiary, terminal alkynes, etc. react with Grignard reagent to form an alkane corresponding to the alkyl or aryl group of Grignard reagent. RMgX plus HB giving RH plus MgBx, where B is OH, OR, SR, OCOR, NH2, NHR, and R2. For example, CH3MgI plus HOH giving CH4 plus MgOHI. CH3MgI plus HOC2H5 giving CH4MgOC2H5I. CH3MgI plus HOC6H5 giving CH4 plus MgOC6H5HI. CH3CH2MgBr plus acetic acid giving ethane plus CH3COMgBr. Methyl magnesium iodide giving with reaction with ethylamine giving methane plus MgNHCH2 CH2H5I. CH3MgBr plus SCH2 CH3 giving methane plus MgSCH2 CH3Br. Since methane is evolved quantitatively when CH3MgI is treated with compounds containing active hydrogens, therefore these reactions can be used for the estimation of OH and H2SH groups in organic compounds. The method employed is called Zerivit-Knopf's method. Aryl magnesium halides also behave in a similar manner. When phenyl magnesium bromide reacting with water, it gives benzene plus MgOHBr. By action with reactive alkyl halides, Grignard reagent react with reactive alkyl halides such as tertiary butyl chloride, benzyl chloride to form alkenes. Grignard reagent plus alkyl halide giving alkene plus MgX2. CH3MgI magnesium iodide plus tertiary butyl chloride in the presence of dry ether giving neopentane. And ethyl magnesium bromide with the reaction with benzyl chloride in the presence of dry ether gives 1-phenyl propane. Second is the reaction with alkenes. Grignard reagents being weak nucleophiles do not react with simple alkyl halides. However, compounds containing more reactive halogens such as allyl iodide react with them giving alkenes. For example, allyl iodide plus CH3MgI giving 1-butene plus MgI2. Third is with alkynes. Grignard reagents react with terminal alkynes forming alkynyl Grignard reagents which upon treatment with alkyl halides give the higher alkynes. For example, propyne with methyl magnesium iodide giving propenyl magnesium iodide. Fourth is the reaction with primary alcohols. By action with ethylene oxide followed by hydrolysis, Grignard reagents react with ethylene oxide to form addition products which on hydrolysis with dilute HCl forms primary alcohols containing 2 carbon atoms more than the alkyl halide. Ethylene oxide plus Grignard reagent giving addition product which hydrolyzes and giving primary alcohols plus MgOHX. Ethyl magnesium bromide plus ethylene oxide gives addition product which hydrolyzes to give 1-butanol. Phenyl magnesium bromide plus ethylene oxide giving PHCH2CH2OMgBr which hydrolyzes and giving 2-phenyl ethanol plus MgOHBr. Second is by action with formaldehyde followed by acidic hydrolysis. When treated with formaldehyde, Grignard reagent forms an adduct which on hydrolysis with dilute HCl gives a primary alcohol. So when formaldehyde reacts with Grignard reagent, it gives addition product which hydrolyzes to give primary alcohol. Formaldehyde reacting with ethyl magnesium bromide giving addition product which finally gives N-propyl alcohol. By action with oxygen, primary alcohols are formed by passing dry oxygen through the solution of Grignard reagent followed by acid hydrolysis of the resulting addition product. For example, N-propyl magnesium bromide reacting with oxygen giving CH3CH2CH2GBr which hydrolyzes to N-propyl alcohol. And secondary alcohols by action with aldehydes other than formaldehyde followed by acidic hydrolysis. Acetaldehyde on reaction with CH3MgI giving addition product which on hydrolysis give isopropyl alcohol. Similarly, acetaldehyde on reaction with phenyl magnesium bromide gives an addition product which hydrolyzes to 1-phenyl ethanol. By treating an excess of a Grignard reagent with ethyl formate, the reaction takes place in 2 steps. Grignard reagent first react with ethyl formate to form an aldehyde which in turn react with another molecule of a Grignard reagent to give an adduct which yields a secondary alcohol on hydrolysis. Ethyl formate reacting with Grignard reagent to form addition product unstable and giving aldehyde, which upon reaction with RMGX giving an addition product which upon hydrolysis gives secondary alcohol. Similarly, ethyl formate on reaction with ethyl magnesium bromide gives an addition product which gives propanol after removing MgOC2H5Br, which on treatment with ethyl magnesium bromide gives an addition product which on hydrolysis gives 3-pentanol. Tertiary alcohols by action with ketones followed by hydrolysis. Ketone reacting with R.MgX gives CRR-OMgX giving tertiary alcohol. For example, acetone giving C2H5 on reaction with C2MgH5Br gives CH3 whole twice COMgBr C2H5 which on hydrolysis gives 2-methyl 2-butanol. A tertiary alcohol having at least two similar alkyl groups may be prepared by the interaction between an ester rather than the forming ester and an excess of Grignard reagent. The reaction proceeds in two steps. Ester reacting with Grignard reagent gives an additional product which gives ketone. Again, this ketone reacts with RMGX, giving a tertiary alcohol on hydrolysis of addition product. For example, ethyl acetate on simply reacting with CH3MgI gives an additional product which yields acetone after removing MgOC2H5I from it, and which on further reacting with CH3MgI gives 2-methyl-2-propanol after hydrolysis. Third, by the reaction with acid chlorides and anhydrides, Grignard reagents 2 moles react with acid chlorides or anhydrides to give addition products which upon acid hydrolysis gives tertiary alcohols. Acid chlorides plus Grignard reagent gives additional product unstable which removes MgXCl and giving ketone. For example, acid anhydride react with RMgX gives ketone, and the addition product is unstable and RCOMgX removes, and again ketone forms which on reaction with RMgX gives an addition product which upon hydrolysis gives a tertiary alcohol. For example, acetyl chloride reaction with CH3MgBr gives an addition product which removes MgBrCl from it and gives acetone which on reaction with CH3MgBr and second hydrolyzing gives tertiary butyl alcohol. Aldehydes. When a Grignard reagent is treated with ethyl formate, an aldehyde is formed. However, with excess of Grignard reagent, the product obtained is a secondary alcohol. Ethyl formate on reaction with RMGX giving an additional product which on hydrolysis gives aldehyde. Ethyl formate with reaction with ethyl magnesium bromide gives an additional product which on hydrolysis gives propanaldehyde and MgOC2H5Br. Second, while aldehydes are obtained in the better yield if ethyl formate is employed instead of ethyl formate. This is so nice since the formation of acetyl in this case prevents the formation of a secondary alcohol. Aldehydes can also be obtained by the interaction between a Grignard reagent and hydrogen cyanide followed by hydrolysis of adduct form. HCN plus Grignard reagent gives an addition product which on hydrolysis gives aldehyde plus MgOHX. Ketones by treatment with alkyl cyanides followed by acidic hydrolysis. For example, acetonitrile with reaction with ethyl magnesium bromide gives CH3C double bond and MgBrC2H5 which on hydrolysis gives ethyl methyl ketone or 2-butanone. CH3Cn plus reaction with benzyl magnesium bromide gives CH3C double bond and MgBrCH2PH which on hydrolysis gives 1-phenyl-2-propane known plus MgOHBr. By action with acid chlorides, as discussed on page 83, equimolar amounts of a Grignard reagent and acid chlorides gives an addition product which forms ketone on hydrolysis. If Grignard reagent is used in excess, tertiary alcohols are obtained as ultimate products of the reaction. Acid chlorides on reaction with RMgX gives a ketone, which on further reaction with RMgX gives a tertiary alcohol after hydrolysis in the second step. Monocarboxylic acids. Grignard reagent interact with dry ice, solid carbon dioxide to form additional products which on hydrolysis, acid hydrolysis to give monocarboxylic acids. Grignard reagents plus carbon dioxide gives an additional product which on hydrolysis gives monocarboxylic acid. CO2 treatment with CH3MgI gives CH3C double bond OMgI which on hydrolysis gives acetic acid. CO2 on reaction with phenyl magnesium bromide gives PHCO double bond OMgBr which on hydrolysis gives benzoic acid. Esters by action with ethyl chloroformate equimolar amounts of Grignard reagent. Equimolar amounts of Grignard reagent and ethyl chloroformate react to form higher esters. जैसे कि ethyl chloroformate when react with Grignard reagents forms an additional product which gives higher ester. For example, ethyl chloroformate reaction with CH3MgX gives an additional product which removes MgXCl and gives ethyl acetate. 12th is thioalcohols. Grignard reagent react with sulfur to give an additional product which gives a thioalcohol on hydrolysis. RMgX plus sulfur giving additional product which on hydrolysis gives thioalcohols. Phenols. Aryl magnesium halide react with oxygen to form additional products which upon hydrolysis gives phenol. Phenyl magnesium bromide which react with oxygen to give in the presence of dry ether to give phenoxy magnesium bromide which on hydrolysis gives phenol. Alkyl cyanides by interaction of Grignard reagent 1 mole and cyanogen chloride of cyanogen. Reaction of RMgX with cyanogen chloride gives alkyl cyanide plus MgXCl. Excess of Grignard reagent is avoided since it reacts further with alkyl cyanides to yield ketones. Primary means Grignard reagent react with chloramine to form primary means, and RMgX plus reaction with chloramine gives RNH2. And ethyl magnesium bromide on reaction with an H2Cl give ethylamine plus MgBrCl. Reasonable yields of primary amine is obtained only with Grignard reagents containing tertiary alkyl groups. Primary amines can also be prepared in satisfactory yields by the action of Grignard reagent chloride or bromide but not iodide on O-methyl hydroxylamine. Now coming on to the limitations of Grignard reagents. Grignard reagents suffer from following limitations. Grignard reagents are sensitive to moisture, oxygen and carbon dioxide and hence must be protected from them. This makes the handling of Grignard reagents difficult. Grignard reagents cannot be prepared from alkyl halides containing other reactive functional groups such as OHSH, NH2C double bond OH, CHO, CO, COR, and since they all react with them, only alkyl halides containing a few other groups such as ROR, ARX can be used to form Grignard reagents. And generally, branching of the carbon chain near the functional group prevents reaction probably due to the steric hindrance. For example, CH3MgBr plus CH3MgI doesn't react with di-tertiary butyl ketone. Similarly, if the Grignard reagent contains large alkyl group, the reaction is sometimes prevented again due to steric hindrance. For example, isopropyl methyl ketone react with CH3MgI but not with tertiary butyl magnesium chloride. Compounds which are capable of phenolization liberate hydrogen with Grignard reagents. For example, ethyl acetoacetate on equilibrium within all forms in reaction with CH3MgI gives enolized ketone. Fifth is nitro compounds cannot be used in Grignard resynthesis since they oxidize the Grignard reagents. Despite the above limitations, Grignard reagents are still the most important tools in organic synthesis. Organozinc compounds. Although organozinc compounds of type R2Z are not commonly used in organic synthesis, they are particularly useful when milder reagents are required. Methods of formation. Following methods are used from alkyl halides. Alkyl iodides react with zinc copper couple in highly boiling ether to form alkyl zinc iodides, which upon subsequent distillation in an atmosphere of CO2 undergoes proportionation to dialkyl zinc compound. Ri plus zinc giving R2ZnI, and which on CO2 distillation gives R2Zn plus Zni2. C2H5 whole twice I giving reaction with 2Zn gives C2H5Zni, and CO2 distillation gives diethyl zinc. Organoaluminium compounds. Treatment of trialkyl aluminium with zinc chloride gives dialkyl zinc compound. This method forms the basis of laboratory preparation of these compounds. Physical properties. Dialkyl zinc compounds have linear geometry due to sp hybridization of zinc atom. They are non-polar, low boiling liquids or low melting solids soluble in organic solvents. Lower zinc compounds are highly inflammable in air and hence usually prepared and used under CO2 atmosphere. Chemical reactions of organozinc compounds are similar to those of the Grignard reagents, with the only difference that they are less reactive. For example, they do not react with CO2 and react only slowly with cyanides, ketones, and esters. Some important chemical reactions of dialkyl zinc are discussed below. First is the reaction with water. They readily react with water forming alkanes. For example, R2Zn reaction with water gives RH and adducts. Second reaction with alkyl halide. Dialkyl zinc compound do not react with primary and secondary alkyl halide. They react only with tertiary alkyl halide to form alkanes containing quaternary carbon atom. For example, tertiary butyl chloride reaction with dimethyl zinc gives neopentane. Third is reaction with acid chlorides. They react readily with acid chlorides to form ketones. For example, diethyl zinc plus acetyl chloride gives butanone on removal of C2H5Zn from adduct. Ketones are obtained in good yields because dialkyl zinc compounds react very slowly with them. Third is Reformatsky reaction. When an aldehyde or a ketone is added to the solution of an alpha haloester in the presence of a zinc, an organozinc compound is first formed, which then adds to the carbonyl group in a manner similar to the Grignard reagent reaction to form a beta hydroxyester. This reaction is called Reformatsky reaction and is a useful method for preparing beta hydroxyesters, acids, derivatives. Ethyl bromoacetate reaction with zinc in the presence of dry ether first gives organozinc compound, which further react with the acetaldehyde to give an addition product, which on hydrolysis gives ethyl beta hydroxybutyrate, that is a beta hydroxyester. Similarly, PHCHO on reaction with ethyl bromoacetate in the presence of zinc ether and finally hybridizing in the second step gives ethyl beta hydroxy beta phenyl propionate. Iodomethylene zinc iodide. Iodomethylene zinc iodide is an important organozinc compound and is obtained by the action of zinc copper coupled on methylene iodide. CH2I2 plus zinc in the presence of diethyl gives iodomethylene iodide, which reacts with olefins to form cyclopropane derivatives. This reaction is called Simon-Smith reaction and is used for the preparation of cyclopropane derivatives. The addition reactions occurs in a stereospecific syn manner according to following concerted mechanism. First is butene. Cis butene to butane gives a transition state which further gives us 1,2-dimethyl cyclopropane plus zinc iodide. Now coming on to organolithium compounds. Compounds in which lithium atom is directly bonded to a carbon atom are called organolithium. For example, methyl lithium, ethyl lithium, N-butyl lithium, phenyl lithium. Organic lithium compounds are more reactive than Grignard reagents and also used undergo a few additional useful reactions. Therefore, they are widely used in organic synthesis these days. Formation of alkyl lithiums. By reaction of an alkyl halide with lithium, alkyl lithiums are generally prepared by treating an alkyl halide with lithium in hexane, benzene, or any other hydrocarbon solvent at a low temperature in an inert atmosphere of nitrogen or argon. For example, alkyl halide in the reaction with lithium gives trihexene RLi plus lithium halide. That is methyl bromide on reaction with lithium in the presence of trihexane giving methyl lithium plus lithium bromide. For the preparation of alkyl lithium, hydrocarbon solvents are preferred over ether since the use of ether not only encourages Wood's reaction but also react with it. For example, diethyl ether in reaction with n-butyl lithium gives butane and finally gives ethylene. By metal-metal exchange, alkyl lithiums can be readily prepared by the replacement of one metal by another. For example, dimethyl mercury on reaction with lithium in the presence of ligroin and 338 Kelvin gives ethyl lithium plus mercury. Chemical reactions of alkyl lithium. Carbon lithium bond is more polar because electronegativity difference is 1.6 than carbon magnesium bond. Electronegativity difference is 1.3. Therefore, alkyl lithiums are more reactive than the Grignard reagents. Except a few differences, their chemical behavior is similar to that of Grignard reagents. Some of their important chemical reactions are discussed below. Resemblance with Grignard reagents. They resemble Grignard reagents in most of their chemical reactions. For example, formation of hydrocarbons. Like Grignard reagents, they react with compounds containing active hydrogen to form the corresponding hydrocarbons. For example, methyl lithium uses water giving methane. Second is formation of primary, secondary, and tertiary alcohols. Primary alcohols by reaction with formaldehyde. Formaldehyde in reaction with alkyl lithium in the presence of hexane gives additional product which on hydrolysis gives primary alcohol. Like Grignard reagent, alkyl lithium compounds also react with ethylene oxide to form primary alcohol containing two carbon atoms more than the starting alkyl aryl halide. Phenyl lithium plus ethylene oxide in the presence of hexane giving PHCH2CH2OLi which hydrolyzes to give a 2-phenyl ethanol. Secondary alcohols. Action with aldehydes other than formaldehyde. Acetaldehyde reaction with methyl lithium in the presence of hexane giving CH3CHOLi CH3 which on hydrolysis gives isopropyl alcohol. Tertiary alcohol by action with ketones. Acetone plus CH3Li in the presence of hexane gives neopentyl alcohol. On hydrolysis, neopentyl oxide, which on hydrolysis gives tertiary butyl alcohol. Formation of ketones by action with any orthoester other than orthoformic ester alkyl cyanide, ethyl orthoacetate in the presence of hexane, giving CH3C, CH3, OC2H5 whole twice, which on hydrolysis gives acetone plus ethanol. Acetonitrile plus ethyl lithium in the presence of hexane giving CH3C11Li, CH2CH3, which on hydrolysis gives butanol plus ammonia plus lithium hydroxide. Reaction with aryl halides. Aryl halides undergo nucleophilic substitution reactions by elimination, addition, or benzene mechanism. For example, O-fluoroanisole on reaction with phenyl lithium gives benzene, which on reaction with phenyl lithium gives 3-phenyl anisole. 1-chloronaphthene on treatment with phenyl lithium gives naphthine, which on phenyl lithium reaction gives 1-phenyl naphthalene plus 2-phenyl naphthalene. Eighth, reaction with heterocyclic compounds. Heterocyclic compounds undergo nucleophilic substitution reactions by bimolecular displacement mechanism. For example, pyridine in the presence of phenyl lithium undergoes nucleophilic aromatic substitution to give 2-phenylpyridine plus lithium hydride. Quinoline on reaction with CH3CH2CH2 whole twice, CH3CH2 whole thrice Li giving 2N-butyl quinoline plus gives 2N-butyl quinoline plus lithium hydride. Second is difference from Grignard reagents. Organolithium compounds being more reactive than Grignard reagents undergo some additional reactions are discussed below. Action with carbon dioxide. Grignard reagents yield carboxylic acids with carbon dioxide while organolithium compounds yields ketone. Carbon dioxide on reaction with hexane giving RC double bond OLi, which on reaction with RLi gives an adduct, which on hydrolysis gives unstable adduct, which gives a ketone further. Action with carboxylic acids. Alkyl lithium compounds react with carboxylic acids, yielding ketones as the main product. Grignard reagents, on the other hand, give alkanes or arenes corresponding to the alkyl or aryl group of the Grignard reagent. Benzoic acid in the presence of methyl lithium in the presence of hexane gives C6H5C double bond OLi CH3Li, which react further hydrolysis to give unstable acetophenone. Third is the addition of carbon-carbon double bond. Unlike Grignard reagents, organolithium compounds add to simple alkenes to give a mixture of compounds. The addition occurs at a high pressures 100 to 500 atmospheres. RLi plus ethylene in the presence of hexane give RCH2CH2Li, with which on ethylene reaction with RCH2 thrice whole 4Li, that is CH3Li plus ethene gives in the presence of hexane gives CH3CH2 whole twice Li, which on reaction with ethene gives CH3CH2 whole 4Li, which on reaction with ethylene again, etc. etc. Formation of tertiary alcohols. Organolithium compounds, being more nucleophilic and smaller in size than the corresponding Grignard reagents, add to sterically hindered ketones to form sterically hindered tertiary alcohols. Grignard reagents, on the other hand, do not give such addition reactions. For example, isopropyl lithium adds to diisopropyl ketone to yield triisopropyl carbinol. Isopropyl lithium diisopropyl ketone in the presence of dihexane gives CH3 whole twice CH whole thrice COLi, which on hydrolysis give triisopropyl carbinol. In contrast, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected tertiary alcohol is not formed. Instead, reduction of the ketone by the Grignard reagent occurs to give diisopropyl carbinol and propylene. CH3 whole twice CH, C double bond O, CH3 whole twice CH. In the presence of again CH3 whole twice CH MgBr gives diisopropyl carbonol plus propylene. Fifth is the reaction with alpha-beta unsaturated carbonyl compounds. Organolithium compound, being more nucleophilic, predominantly undergo 1,2 addition reactions to give alpha-beta unsaturated carbonyl compounds, whereas Grignard reagents give mainly 1,4 addition products. For example, benzyl acetone in the reaction with CH3Li gives 1,2 addition product, which on hydrolysis gives 2-methyl-4-phenyl but but 3-into-ol. And benzyl acetone on reaction with methyl magnesium bromides gives 1,4 addition product, which on hydrolysis gives 4-phenyl pentane. You can see from this reaction. So thank you so much.